we'll move on. Next is Victoria Strait, and she'll be telling us what we can learn about galaxies and cosmic dawn before JWST.
All right. Yeah, thank you guys for having me. I'm Victoria, and I'm a grad student at UC Davis, working with Marusha Brodach as my main advisor, but I've also had other important mentors, including Brian Lameau, Dan Coe, Deborah Policia, and several others. And I'm going to be moving actually in a few months to the Cosmic Dawn Center in Copenhagen, so I feel a little bit kind of in a gray area right now, but I'm going to be telling you about galaxies at cosmic dawn using Hubble and Spitzer mainly, and a little bit of with Keck at the end. There we go. So I know that we're all here because we are interested in cosmic dawn, and maybe we're already interested in galaxies at cosmic dawn. But my personal reasons for why they're interesting are listed here. So first, they're progenitors of all galaxies that we see today, including the Milky Way. They're hosts to the universe's first stars. They're likely responsible mainly for the reionization of neutral hydrogen in the IgM. And I think my favorite reason right now is that they likely have extreme stellar populations, which makes them laboratories for sort of, new mechanisms of star formation or things like that. And so with observations that we've heard about, this morning and yesterday, we can constrain a lot of things on top of just basic stellar populations, including ionization and ionizing bubble sizes, kinematics of gas in the galaxies, and even the first star formation, possibly POP3 components. And so I'm interested in, getting a better handle on all of these things that I have listed here: metallicity, size, age, dust, etc., on top of stellar mass, star formation rate. And I'm taking the approach of using lensing. So I've worked with a few different lensing campaigns, but the one I've worked with the most is the Reionization Lensing Cluster Survey. And this is a survey of 41 massive galaxy clusters that were chosen. I'm plotting here the Planck mass and redshift. They were chosen to just be sort of high redshift and very massive, so that there are lots of high redshift galaxy candidates behind them. Dan Coe PI'd 188 HST Treasury program for these, and my advisor Marusha PI'd a very large, over 1,000-hour Spitzer program. And so there's lots of science being done in RELICS that I won't talk about, like lensing, supernovae, and galaxy cluster scaling relations. I'll mostly focus on the high redshift because that's what I do, and it's the main goal of the survey. So here I'm plotting the high redshift sample. So there were 21 selected redshift candidates. So I'm showing magnitude here in redshift, and the RELICS candidates are plotted in pink on top of some other high redshift galaxy surveys. And these are just Lyman break selected photometry only candidates. And there are a few spectroscopic follow-up programs on these galaxies. Our group at Davis has been using Keck, Mossfire, Elris, and Demos to look at a few of the clusters in RELICS, and there's also folks using Muse and ALMA to follow these up. And like I said, I'll present a Keck result at the end, but I mostly have spent time working on Spitzer observations, imaging from IRAC, just because this is important for doing SEB fitting. So this is just a random example galaxy from a Hubble Frontier Fields cluster, AVAL 370. I'm plotting magnitude versus wavelength here, and then the black points are the data, the photometry from Hubble, and then the blue line here is a best fit BCO3 template. And the point of this slide is just to show you why Spitzer is important. So Spitzer at redshift 6, the rest frame optical falls into the near infrared where Spitzer probes. And so over here, I'm showing the distributions of stellar mass, star formation rate, age, and specific star formation rate with only the Hubble fluxes of this galaxy. And then when we add Spitzer, we can constrain, the light from old stars and emission lines and get a much better handle on these galaxy properties. Oops. And so there were 300 galaxies in the sample, and these are the 3 that I've kind of chosen to highlight and tell you about. The first sort of exciting thing to come out of the sample was this spatially resolved redshift 10 arc. This is exciting because anything extended at high redshift is exciting. You can even see separate clumps in this. And unfortunately, it was very blended with a bright neighboring galaxy in Spitzer. So we could only get upper limits in flux, but it was enough to securely put the redshift at redshift 10. So this is, we hope to follow this up and learn more about it, but it is securely a lensed redshift 10 galaxy. The one in the middle here was a redshift 8.4 galaxy discovered behind Abell 1763. And the interesting thing about this galaxy is that it shows evidence of a Balmer break, which means that there are old stars in the galaxy. It's evolved, meaning, it's been around for around a couple 100 million years, which is significant at redshift 8 because the universe is only a few 100 million years old. And that means that the stars in this galaxy must have started forming very early. So this is sort of an indirect way to put a constraint on the first star formation. And then the last galaxy over here is one behind Planck 287, and it's showing an elevated channel 1 Spitzer flux, which we believe, like many others have seen, points to extreme O3 H beta emission, at least 1,000 angstroms in equivalent width. And this galaxy is at redshift 6.8. So we're, of course, not the only ones to. Lots of other people are seeing this sort of galaxy popping up in our sample too, and these 2 galaxies are just sort of examples of lots of other similar ones that we found. So we found several other Balmer break galaxies and several other extreme O3H beta emission galaxies. And so, since I don't have time to tell you about all 300 galaxies, these are some diagnostic plots of luminosity, stellar mass, and age. I was able to release a public catalog of all the data for 2/3 of the galaxies that I could extract Spitzer fluxes from, and so that's available at my website if you're interested. It has Hubble and Spitzer fluxes and stellar population fits with lots of different parameters from 2 very different SED fitting methods. And so one other interesting result to come out of this this survey was some work done by an undergrad at UC Davis, Chloe Neufeld. She's been using a code called Lenstruction to de-lens all of the high redshift RELICS sources and then measure their sizes. And so here we're plotting half-light radius in kiloparsecs versus magnitude, comparing to some redshift 1 to 3 sources in purple here, and then to Richard Bowen's 2017 size results here in the triangles. And our results are in stars. And so you can see that compared to Bowen's Hubble Frontier Fields results, ours are brighter, but we are finding quite small galaxies. And so this project is with the main goal of looking for highly star-forming compact galaxies that could likely be Lyman continuum leakers. And I have to put in a plug for Chloe. She's applying to grad school this year in the US and in Europe, and she's an excellent student, so look out for her application. And so the last result from RELICS that I'll talk about is this galaxy, the dichromatic primeval galaxy at redshift 7. This thing we detected in Lyman alpha with LRIS on Keck, and saw that it had a huge Lyman alpha equivalent width of 200 angstroms, and it was spatially resolved. And so this is kind of at odds with the SED here, which shows very red beta slope and bright IRAC fluxes. And it's also quite faint. It's 0.3 L star, and so this galaxy was puzzling to us. And it also made us think of, these other named galaxies on this plot, CR7, Masosa, Cola 1. And so you can see on this Lyman alpha equivalent width versus UV luminosity, DP7 is the strongest, or one of the strongest Lyman alpha emitters, one of the faintest and one of the reddest. So this is the reddest. It's colored by UV beta slope. And so compared to some of these other named galaxies, we think it's similar. Maybe it's carved out its own ionized bubble, or it's a fainter galaxy within one, possibly could have POP3 or metal core component. And several of these other galaxies also point to possible evidence of a merger or accretion event. And so upon a little bit of a closer look at our HST data, we saw that DP7 does in fact have two distinct components in the UV, and with almost significantly different beta slopes. So it seems that this could possibly be evidence for a merger and accretion event as well. And so we have an HST proposal in to nail these beta slopes down a little bit, and we have an ALMA proposal in to look at the C2 in the galaxy to study the ISM, and we have a denied James Webb proposal that I won't give up on. So I think I'll just leave my slide up here and take questions.
Thank you, Victoria, for a nice talk. We'll wait 20 seconds.
Thanks, Victoria. So I'll ask your first question, which is, how do you model dust attenuation in your SED fitting?
Yeah, so we do SED fitting with two different methods. They're very different, and I can go into more detail than I showed right now. But so with the first method, we use easy to constrain redshift, and then we use BCO3 templates, which just assume some kind of dust law. And I think we chose SMC for that one. And I think for the other one, we use bagpipes to model to do SED fitting for a second method, and we assume dust around the birth cloud and a Calzetti dust law.
Okay, next question is, what is your favorite star formation rate history in your SED fitting?
Sorry, I think I broke up here a little bit. Did you say what is my favorite star formation history?
Yes, in your SED fitting.
Okay. So I think my favorite one right now is we're just using a variable star formation history that allows increasing, decreasing, and constant, just for the freedom of it. But at high redshift, it ends up not mattering that much because there isn't much time.
So how do you account for blending with the cluster galaxies, and how much of an issue is crowding in the cluster cores and the IRAC imaging?
Yeah, so I use a code called tphot to account for blending, which uses like a template-based approach to model each galaxy in the field, and it uses Hubble as a prior, and then it degrades that resolution to Spitzer resolution, and then we can kind of fit for the Spitzer fluxes, although it's not perfect. So I think that in one of my slides, I said, we only have 200 of the 300 galaxies Spitzer fluxes, and that's because 100 of them were, too severely blended by cluster members. So cluster fields, this is hard to do in cluster fields, so we can't always get Spitzer fluxes.
Okay, so you have a couple more questions in Slack to address when you get a chance. Thank you very much again for a nice talk.